Thank you very much, Maggie, and thank you very much to Pinfa for having IDTechX on. Hi everyone, thanks for coming. My name is Conrad, Senior Technology Analyst at IDTechX, and today's webinar I'm going to be talking about the trends in battery storage, battery energy storage system, or BESS as I'll call it from here on, thermal management and fire and explosion protection. So just a little bit of a background on IDTechX for those that don't know. I won't spend too long on this, but for 26 years now, the company has been providing independent market research, consulting services, and subscriptions on a variety of emerging technologies to clients in over 80 countries. And so as well as energy and battery storage, we of course cover things like electric vehicles, hydrogen, other decarbonisation topics, and then other adjacent topics such as 3D printing, advanced materials and critical minerals, robotics and autonomy, sustainability and wearable technologies, and the list goes on. The reports that we cover include things like technology assessments and benchmarking, scouting new technologies. We profile companies in person and over the phone. We size markets and forecast them and provide strategic advice to our customers. And so why IDTechX? We provide a deep technical and market understanding in our market reports, and our assessments determine the true value and potential of the technologies for each industry that we cover. We're connected to over 250,000 global contacts, and our research is gathered through interviews, site visits, and global event attendance. We focus on the application of technology innovations, and so we assess these technologies and their applications to provide the complete picture of opportunities across essential industries. And today's webinar, I'm going to be drawing insights from our upcoming report that will be published in the next couple of weeks on thermal management, fire and explosion protection for BESS. And in this webinar specifically, I'll first give an introduction to the BESS market and some of the key trends to give you a good understanding of that before we dive into then an introduction onto thermal runaway, discussion of the key BESS safety regulations, an outline of then active and passive BESS fire safety measures and technologies, then a little bit of an assessment on thermal management and fire protection materials, and then we'll have a review at the end of the major trends for the BESS thermal management and fire safety market. And after this, we'll have time for a quick Q&A as well. I'm happy to answer some of your questions. So firstly, I'll give you an introduction to the BESS market to provide some context for the thermal management and fire protection side of things. So energy storage technologies can be classified into 5 key groups, and this includes chemical, electrical, thermal, mechanical, and electrochemical or battery storage. And all of these technologies come with their own pros and cons, and there's no silver bullet technology which ticks all the boxes here on the right-hand side of the screen. Investors and customers will be weighing up all of these considerations, such as system lifetime, branch efficiency, safety, capex, or levelized cost of storage, if you can decouple the energy and power, what's the minimum economical size per project that makes sense to develop a certain technology at commercial scale, and any challenges that may come with generating revenues from operating these assets. But when we consider lithium-ion BESS or battery energy storage systems, their capex, their cost continues to drop, and safety continues to remain a high priority. These systems are prone to thermal runaway and fire and explosion risk driven by their flammable electrolyte, which we've annotated here on the screen. This contains flammable and toxic chemicals such as ethylene carbonate and lithium hexafluorophosphate. The latter chemical can decompose into hydrogen fluoride gas, and then this can react with other chemicals found in the cell to produce flammable and explosive hydrogen gas. Many of the other energy storage technologies, however, do offer a safety advantage due to the lack of flammable electrolyte, though a typically higher cost. And when we look at the global BESS market recently in the last few years and the global lithium-ion market, these continue to grow rapidly. And in 2023, we saw over 900 gigawatt hours of lithium-ion battery demand across the 3 key market sectors, which include electric vehicles, energy storage systems, and consumer electronics. And with this, BESS has started to take up a growing proportion of the overall lithium-ion battery demand globally. With the slowdown that we've seen in electric vehicle markets this year and changes at the regulation level, especially in the US, for incentives to develop energy storage, this trend will be expected to continue. And so over the last few years, again, we see China and the US being responsible for most BESS installations in the past few years. However, other countries are showing the early signs of large and emerging grid-scale BESS markets, which could shake up market outlook and the global outlook. And those countries include, for example, Australia, India, Chile, and Italy. Some other emerging activity which we've noticed specifically this year is in Poland, Japan, and Korea, and the Middle East as well. Importantly, this year, with changes to US legislation in the One Big Beautiful Bill Act, or OBBB, from our analysis at IDTechX, we anticipate that US LFP cell prices could potentially be competitive with Chinese imported LFP cells going into 2026. An LFP, for those that aren't familiar, is lithium iron phosphate. It is the typical cathode chemistry that is used in lithium-ion BESS technologies. As well as that, we're starting to see the localization of US cell supply and material supply, and that's being observed now at a sort of very early stage. But we'll be happy to talk a bit more about that in the Q&A. So when we look at the three core BESS market segments, depending on the battery application, so whether this is residential, commercial, and industrial or grid scale, the properties of the battery, the services which they provide, and the thermal management, fire, and explosion protection strategies will differ. When we look at residential batteries, these are typically smaller, 1 to 15 kilowatt hours in energy capacity, are used for things like self-consumption of renewable energy and improving one's energy security at home. C&I batteries, or commercial and industrial, can range from anywhere sort of 10 kilowatt hours up to 20 plus megawatt hours. And these offer very versatile applications that can be used simultaneously or at different times, depending on what the customer wants to do with that battery. And this could be things like peak shaving electricity, maximizing the use of locally generated on-site renewables like rooftop solar, for instance. Grid services can also be provided by those batteries and so on. And we see data centers being a sort of key growing application going into the future for these sorts of batteries. Grid scale battery storage technologies, these can be anywhere from 1 megawatt hour into now the multi-gigawatt hour scale. There are individual projects that are sort of 3+ gigawatt hours with hundreds of these sort of battery storage containers on site, which you can see with this photo here. And these are typically used for energy shifting applications where the owner and the operator of the battery will take advantage of price arbitrage, so changes in electricity price to sell electricity when it's more expensive and charge the battery when it's cheaper. And these owners of these batteries can also be paid back or remunerated for the ancillary grid services that the battery provides, things like frequency and voltage regulation, black start, and so on. One of the key trends that we've noticed and will definitely continue to be happening is the shift to the lithium iron phosphate chemistry and away from the nickel manganese cobalt or NMC chemistries in lithium ion BESS. And the shift to LFP is driven by its lower cost, its longer cycle life, and generally speaking, its lower risk of undergoing thermal runaway in the first place. The main trade-off with using LFP over NMC is the energy density of the cells and therefore the system and therefore the project. So this data here incorporates overall global annual installations in the respective years across the key three markets I just discussed. So while energy density is more of a factor in electric vehicles as it is than it is in energy storage, it is still something that has to be considered. And with this consolidation towards LFP, battery storage manufacturers and developers are trying to find ways to improve the energy density of their overall systems, whether this can be done at the cell level or at the system or even project level. And as I said, as it's not so crucial, we're also seeing these sorts of trends in an increase in larger cell form factors, prismatic cells that are kind of cuboid in shape. And with these larger cells, you have a higher proportion of the container being attributed to cells rather than dead space, thermal management, or power conversion systems like inverters. A higher proportion of the cells might also be attributed to active materials, and this increases the cell level energy density. So with that, you then have these higher system level energy density technologies being installed in 20-foot containers. And this can ultimately help for potential cost savings for customers at the project and transportation level, as you ultimately need fewer containers to reach a certain project capacity. What the impact this might have on thermal management is that with a fewer number of cells, because you have fewer larger cells, this might mean you have less passive fire protection materials, which we'll come on to, such as cell spacers being used in the BESS. And what that might mean is that there'll be a larger reliance on active thermal management and fire protection technologies using things like liquid cooling and fire suppressants. So that was your sort of very quick rundown of the battery storage market globally. And hopefully I can move the slide. So now we'll jump into an introduction on thermal runaway and then move into BESS fire safety market impacts and regulations. So as BESS capacities scale and as deployments grow, there is an increased risk of thermal runaway and potential for a larger scale event like a fire or an explosion. And therefore, stricter BESS safety measures are required. But beyond fires and explosion damage risk and risk to personnel, toxic gases can be released as a byproduct due to the battery electrolyte decomposing. And as I said, so that could be things like hydrogen fluoride and hydrogen gas itself. And these gases can pollute waterways and then the environment, of course, then harming wildlife and populations. In 2018, there were a number of battery fire incidents in South Korea, and this led to Korea's market stagnation for BESS, of which it's only now recovering from only 5 years later. However, recently, you might have seen in the news just a few days ago, there was a large-scale fire at a Korean data center where it was believed that a lithium-ion BESS was the source of the sort of thermal runaway propagation. That was where the fire started. And this event ultimately took down hundreds of government services. So the impact is not only to at a sort of financial level or risk of personnel, it also then, if it's tied into a commercial, industrial, or a grid application, can have significant ramifications for the services which the battery is helping to support ultimately. So with this, governments are starting to tighten BESS safety regulations and the respective third parties that may be responsible for those too. But these do vary depending on the country and the region, and this makes it complex for BESS developers to follow consistently. And so global BESS regulations could definitely help to promote a sort of more consistent overview on what those regulations are. So what sort of causes thermal runaway and what are the stages of it? And so BESS failures can stem from a range of different internal and external factors, and this might trigger a thermal runaway event, and in some cases this could lead to a fire as well. So some of the causes of battery thermal runaway include electrical, thermal, or mechanical failures. This could include things like overcharging, heat stress, or damage to the battery itself. And once a failure triggers thermal runaway, it is the gas evolution during the event which causes fires and explosions. And those off gases from the battery cell can include carbon dioxide, carbon monoxide, and fluorine-based gases like I've talked about. These can then react to form explosive and flammable hydrogen gas. And as these gases evolve, pressure builds up within the cell and then the system, and once a critical point is reached, the battery will rupture with the gases potentially igniting. So you can have, of course, then a fire and an explosion happening simultaneously, which can be catastrophic. So a series of recent high-profile BESS incidents has led to increased scrutiny of BESS safety. The map shows here on screen the number of BESS incidents in each region between 2018 and 2024, and this is recorded on the EPRI database. As I touched on, the number of incidents that happened in South Korea led to its market stagnations due to concerns over personnel safety. A spike in US-related incidents mostly has been attributed to poor BESS integration and assembly, with globally most incidents occurring due to manufacturing defects, whether that's at the cell or the system level. Improvements in the training of both manufacturers, integrators, and operators may therefore also help to reduce BESS fire risks. What would also be very helpful and is definitely up for discussion maybe in the Q&A is greater transparency on the root cause of battery failures. This could definitely help the market on the whole. Of course, there are different sort of considerations that have to be made with releasing that information. And so this table shows the key regulations imposed by major countries relating to BESS fire safety. So I'll just walk through some of this. It is quite wordy, I appreciate. So the US leads the way for safety regulations and restrictions on BESS thermal management. And UL regulations are a framework for battery testing and system thermal management strategies. Several regulations fall under UL 9540, which alone acts as a guideline for deployment. However, NFPA, which are fire codes 855, mandates that UL 9540 certification for all US deployments must be made in participating states. The EU battery regulation, which recently came into force, mandates that all battery systems have to have a CE mark for sale on the EU market. This, while it shows the product and the manufacturer is compliant with the EU regulations, it is not a third-party verification on safety, and so it doesn't demonstrate rigorous safety testing and is consequently not valid for BESS deployments in the US. The Chinese government has largely focused on EV battery regulations and recently introduced the GB 38031 2025 regulation, which takes effect in July of 2026. And this essentially mandates the first no fire, no explosion standard for lithium-ion batteries, even during thermal runaway events. And several battery developers, so CATL, BYD, SunGrow are some key ones. These all operate across the EV and BESS markets, and they've begun to integrate the new standards into product development. And the shared EV and energy storage supply chains could ultimately trigger stricter safety standards for BESS on the whole. Overall, current safety standards may not really be that sufficient for large-scale modern BESS deployments. And as capacity of battery systems scale, along with the size of BESS deployments, so do the risks of thermal runaway. But current safety testing and regulatory frameworks like the UL 9540A may not be sufficient to ensure safe BESS deployments and installations. So with that sort of introduction and overview, we'll now dive into a bit more of a discussion on the passive and active technologies that can be implemented to improve BESS safety. And so thermal management and fire protection technologies for BESS can broadly be split into active and passive systems. And the active technologies refer to systems which require power to operate and dynamically respond to risks such as cooling technologies, sensors, fire suppressants, and ventilation. Whilst passive technologies, on the other hand, mainly relate to material systems which do not require external power or activation, and instead they work continuously once built into the system to reduce thermal runaway risk, or they help to control the extent of damage or provide fire retardant properties. And there are many different types of passive materials which can be integrated into BESS for thermal management and fire protection, which you can see here on the left-hand side of your screen. There is a lot of choice. And this table provides a qualitative comparison of these different materials. The pros and cons will each differ depending on the specific products and the application. And when choosing which material to use as a BESS manufacturer, developers must first consider the material application and whether it requires thermally conductive or thermally insulating materials. And so the more thermally conductive materials like polymer foams and phase change materials can be used to aid heat transfer away from the cells and help to reduce hotspot formation within the BESS. However, they do display low temperature resistance since they are conductive materials compared to other materials, and so they therefore do not then typically offer flame retardant barriers or properties. And thermally insulating materials are likely to dominate over thermally conductive materials, with mica and ceramics performing the highest in terms of temperature resistance, and they also work to contain heat spread within the BESS. Aerogels are another interesting and emerging material which is currently limited in adoption, and this is due to its high cost. But we do expect that due to its very high thermally insulating properties and its low thickness, that its adoption will continue to grow in the BESS market over the coming decade. And so all of these materials may see some adoption within a BESS container, depending on the design choice, and we would probably expect the types of materials that are being adopted by different players to evolve over time. And so on the bottom right-hand side of your screen here, cell spaces, these are placed between cells, and these are used to prevent heat propagation across adjacent cells, And it's a simple means of incorporating thermal management materials into the BESS, with mica, ceramics, and foams suited well here. Cold plates are typically integrated for liquid cooling purposes, and these are in contact with the underneath side of the battery modules, which are the sort of black rectangles that you can see here inside the BESS. And to aid in heat transfer away from the cells through the bottom of the module, you can incorporate things like thermally conductive coatings and phase change materials, and these will absorb the excess heat and provide a conductive pathway to the cold plate. And this ultimately aids with heat dissipation and prevents heat spreading from cell to cell. And at the rack and battery pack or module level, insulation and coatings can be incorporated to contain heat spread. Foams, coatings, and insulation materials are typically well suited for this. And in the future, we could expect intumescent coatings to be applied, and these are coatings which form a char upon exposure to heat. However, post-processing to remove the char can be quite challenging. And at the container level, so lining the inside of the container could also be an option. And you could do this with insulation materials, again, to contain heat and prevent flames from reaching outside of the container. And here we could expect materials such as foam, ceramic blankets, and mica to be suited, along with intumescent coatings for advanced flame retardancy. So we've touched on some of the passive materials and what we would expect from that side of things. If we now look at the active technologies, these thermal management systems and technologies typically refer then to cooling technologies, sensors, fire suppressants, and venting. And active cooling technologies can ensure that batteries operate at optimum temperatures. These help to prevent hotspots and temperature gradient being formed across a cell and a pack, which can then ultimately lead to a thermal runaway event or show the early signs of it. And indirect liquid cooling, which relies on the cold plate technology that I mentioned, is the dominant choice for grid scale and CNI BESS deployments in the current market. And this is due to its superior heat efficiency over air cooling. On the other hand, though, air cooling, we would expect it to still be used for some of the lower power demand applications, maybe where there's less sort of frequent cycling and where cost is a greater factor. Immersion cooling is an emerging technique, and this does achieve the highest efficiency cooling, though cost, system complexity, and manufacturing to prevent liquid sort of or coolant leakage to the cells must be considered, and therefore that means it's likely to be a very sort of niche use case where safety is ultimately critical over cost. That could include applications maybe like medical applications, for instance. And preventative technologies are vital to mitigating thermal runaway risk. And while traditional unit level sensors like smoke or gas detectors help to alert operators to a fire event, they can often identify problems too late when the thermal runaway event is already happening. And so there's ultimately opportunity to integrate advanced sensors at the pack or the cell level to detect early off-gassing. And this could enable earlier intervention and system shutdown before a full-scale event occurs. Now, if the gas detection fails, smoke will then trigger fire suppression systems, and these are typically condensed aerosol-based and water sprinklers as well. Though the water sprinklers, so the aerosol-based systems, that's right, they are typically cheaper, but they are largely then ineffective, or rather, sorry, the water sprinklers are largely ineffective against battery fires and reflash. So aerosol systems suppress flames by inhibiting the chemical reactions, but they don't provide active cooling. Many developers therefore typically will pair the aerosol systems with sprinklers to combine flash suppression or flame suppression and cooling, though this comes then at higher cost. And finally, deflagration venting. This is a key safety measure in BESS, and it's designed to release pressure from the building up of off gases and any flames safely during a thermal runaway event. It doesn't prevent failures. Venting helps limit damage when integrated as part of a broader fire and thermal management strategy. Passive vents remain the most widely used option due to its cost effectiveness, but you can also have active vents which are triggered in a different way. And you have these systems that might combine both active and passive venting for greater responsiveness and venting control while balancing cost at the same time. So just to touch on cooling, this is fundamental to BESS temperature control. It ensures that the battery operates within the cell's sort of operating temperatures. It helps to prevent hotspot formation and temperature gradients, which can induce thermal runaway. If the cells can operate within their operating temperatures longer over their lifetime, this extends the lifetime of the cells and therefore the system as well. Liquid cooling, as I mentioned, or indirect liquid cooling, this is emerging as the industry's dominant choice. This is due to its superior cooling efficiency compared to air cooling, helps to extend the cell lifetime. Air cooling is typically less effective compared to liquid cooling, and this would use things like high voltage or HVAC systems. And this its less effective cooling is due to low heat capacity of air compared to liquids. In liquid cooling, you'll typically be using a glycol water mixture. But we would still expect air cooling to be taken up in some of the lower power capacity applications, less frequent power cycling, and particularly sort of in residential and some commercial and industrial applications. Immersion cooling, it can provide some of the most uniform cooling, but it does require very sort of costly coolants. Complex setups and manufacturing also needs to be considered. Okay, and so now for a sort of final outlook before we then hop into a Q&A. So when we look at the system costs for a BESS today and how that's going to change over time, we would expect more of the BESS container to actually be, or its costs to be attributed to the materials and the systems for fire protection and thermal management. And a lot of this is attributed to the fact that the cell cost continues to fall and it will approach a cost floor relatively soon, we would expect, especially in China. Western markets will take a while to catch up. But when we look at the split between the thermal management and fire protection technologies, these represent over 20% of total BESS capex by 2035. Now, the material costs, so things like the mica, the foams that I was talking about, these will remain below 1% throughout the period. Now, this rising share of value, as I said, that's because the battery cell prices are likely to come down, and this makes these other subsystems and materials more significant in the overall BESS cost structure. And therefore, that means that the BESS manufacturers are likely going to start putting pressure on a lot of the materials and the chemicals companies to find ways to reduce the costs of their technologies, whether that is to find more efficient liquid cooling technologies, maybe uses less materials or can cool things more efficiently. And so IETechX would expect the greatest opportunities lie in the sort of cost reduction of the active safety systems, things like sensors, fire suppressants, venting, and cooling. And so when we look then sort of 10 years into the future, by 2036, we would expect the total BESS, thermal management and fire protection material and system market to reach 25 billion US dollars. Most of that, as I said, is attributed to the sort of active systems as opposed to the passive materials. Fire safety systems, as I said, will dominate. That's due to higher system costs and greater component volume required. Liquid cooling is likely to account for the greatest share of market demand due to high efficiency and its rising adoption. And across the BESS market, uptake of the different systems and materials will vary across the grid scale C&I and residential BESS markets. And so, for instance, in a residential BESS, because if you remember one of the earlier slides, the system is physically smaller, you're less likely to be able to incorporate a very efficient and space efficient liquid cooling system. It's more likely to remain on the air cooling side of things. So to summarize then, growing BESS capacities and large-scale deployments, which are now reaching gigawatt-hour scales and levels, amplify the risks and severity of thermal runaway. And this drives the need for stricter thermal management and fire protection strategies. Heightened scrutiny on BESS safety has followed from several high-profile fire incidents, and this raises awareness across the industry. Regulatory requirements around BESS safety are increasing globally, but they vary by region. These are complex to navigate and may not always be legally binding. This can make it very difficult for BESS manufacturers to know how to enter into different markets. BESS thermal management and fire protection approaches can be categorized into active and passive measures and systems. Most of the market value is concentrated in the active fire safety systems due to their higher costs and scale of deployment. Passive thermal management and fire protection materials provide a lowest cost, space-efficient way to mitigate thermal runaway risks. And total BESS thermal management and fire protection material and system market we expect it to be sort of forecast to exceed 25 billion US dollars by 2036. If you are looking for more information, please reach out at www.idtechx.com/research/ES. And this is where you can find our whole energy storage and battery portfolio. And that brings us to the end of the presentation segment of the webinar. I'm very happy now to jump into some questions and answers. Thank you.
Thank you very much.